Bismillah wassalatu wassalam ala rasulillah. Welcome to General Chemistry with Dr. Zainab. Today we are going to solve recitation problems for chapter 6, which is about quantum theory and the electronic structure of atoms. So let's start by problem number 1. What is maximum number of electrons that can have the following set of quantum numbers? So we have here n equal 4 and mn equal -1. So let's start by n equal 4. When we have n equal 4, what are the possible value for L? We know that we have 0, L, and here n -1. And here n is 4. So we have L can be equal to 0, 1, 2, or 3. When L equals 0, what are the possible number for Mn? We know that Mn will be equal to 0. When L equal 1, we know that ML can be equal to -1, 0, and 1. When L equal 2, we know that ML can be equal to -2, -1, 0, and 1. And when L equal 3, we have ML that can be equal to -3, -2, -1, 0, 1, 2, and 3. And here I need to add 2. Okay, so what are n? For n equal 4, we have ml equal -1 when L equal 1. We have ml equal -1 when L equal to 2. And ml can be equal to -1 also when L equal 3. So we have three orbitals that can have the set n equal 4 and ml equal -1. If we have three orbitals, what is the maximum number of electrons? Exactly 2 times 3, meaning 6 electrons. Okay, so the maximum number of electrons is 6. So the answer is A. Okay, so here remember the rules, the principal quantum number n, and we have the quantum number L that is between 0 and n-1, and we have ml here that is between -L and L. So here we have 2 L plus 1 values, okay? And here we have n values for L. So if you apply it and you get all of the number for all of them n equal 4, and for ml equal -1, we know that it's the p, okay? It's the p orbitals, and we know that for p orbitals you have a maximum of 6 electrons. So this is also another way of seeing this exercise. Okay, let's move to problem number 2. What is the energy of 1 mole of photon of microwave radiation with a wavelength of 0.122 meter? So here we know that for 1 photon, the energy is equal to h mu or hc over lambda. So this is for 1 photon. If I have 1 mole, what is the number of photon in 1 mole? You need to remember the definition of the Avogadro number. So in 1 mole, I will have a number of photons. So if I want the energy for 1 mole, I need to do hc over lambda and multiply it by the Avogadro number. Okay, so just remember that this hc over lambda is for 1 photon, and for 1 mole, I have Avogadro number of photon. So I need to multiply this unit by 6.022 10 to the power 23. So let's calculate it. So energy for 1 mole will be equal to h 6.63 10 to the power minus 34 times 3.00 10 to the power 8 divided by lambda here in meter 0.122, and here multiply by the Avogadro number 10 to the power 23. Okay, and this is equal to 0.980 joule, and this is per mole. Okay, so the answer is A. If you calculate only Hc over lambda, you will find 1.63 10 to the power minus 24. But this is for one single photon. Okay. But here we have 1 mole. So you need to multiply by the Avogadro number to get the full energy. Okay, so then don't be confused between one single photon and 1 mole. The definition of 1 mole number, 1 mole of anything is equal to the Avogadro number of that thing. So 1 mole of photon give an Avogadro number of photons. Okay, so let's move to problem number 3. How many electrons are there in all the p orbitals of a vanadium atom? So here we have vanadium atom. First thing to check is what is the atomic number. So Z equal, for vanadium, we go to the periodic table and check Z equal 23. Okay, so we are going to fill the orbitals. So don't forget to remember how you fill them. You know, it's 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And we fill them like this: 1s first, then 2s, then 2p, 3s, then 3p, 4s. Here we have Z equal 3. So we know that it will be 1s2, 2s2, 2p6, 3s2. So far we have 10, 12. So we need to continue. 3p6, 4s. So here 4s2. Okay, and after that it's going to be 3d and 4p. Okay, so here we have 10, here we have 10, we have 3 left, so they will be in 3d. Okay, so 2 to 4 plus 6, 10, 2 to 4 plus 6, 10, 20. Well, it's how many left? Only 3. Okay, and our pair orbital that I feel is 2p and 3p. Okay, and they have each 6 electrons. So the number of electrons in all pair p orbitals are 6 plus 6 equal 12 electrons. Okay, so our answer is A. Okay, so here just remember how to fill the orbitals. So 1s, 2s, 2p, 3s, 3p, 3d. For 1, you have 1s. For 2, 2s, 2p. For 3, you go to d. For 4, you go to f. And g, h, the alphabetic order. Okay, and then you fill them with Z equal to 23. And after you can read what are the p orbitals that are filled, and for each one of them, what is the number of electrons, and you get this answer. Okay, let's move to exercise number 4. Calculate the frequency of the light emitted by a hydrogen atom. So we have hydrogen atom during a transition of its electron from n equal 4 to n equal 1 principal energy level. So here, what are we going to use? We can use the Rydberg equation, okay, or the Bohr equation between 2 different levels. We have the expression, so we know that Hc over lambda, which is E, will be equal for hydrogen atom minus 2.18, 10 to the power minus 18, okay, multiply by 1 over the final one. So here we have initial one, n1 equal 4, and final one, n2 equal 1. So we have n1 square minus n2 square. And here what is asked is the frequency. We know that mu equal c over lambda. Okay, it's coming from c lambda mu. So mu equals c over lambda. So we can get it directly from this formula. C over lambda will be equal to minus 2.18, 10 to the power minus 18 divided by h, and times 1 over final square, initial square minus final square. So we can calculate the frequency mu. So mu equal to minus 2.18 10 to the power minus 18 divided by 6.63 10 to the power minus 34 multiplied by 1 over 4 square 16 minus 1. Okay, and mu will be equal to 3.08 10 to the power 15 second minus 1, or x. Okay, so our answer is A. Okay, so here just use HC, the difference of energy. You can hear delta E, HC over lambda. So it's between 1 and 4. So I have 1, 2, 3, 4. And the electron is transitioning between 4 and 1. And there is a photon that is released with lambda. Okay, so this is delta E. And delta E equal lambda lambda HC over lambda, or H. Yeah. Okay, and this is the formula we get from here. And for a hydrogen atom, we know that it's minus 2.18 10 to the power minus 18, 1 over n1 square final minus 1 over n2 square final, where n1 is initial and n2 is final. Okay, so this is how we solve this. Let's move to problem number 5. Calculate the wavelength for a neon atom moving with a velocity of 10 to the power 5 meter per second. Okay, so we have a neon atom. What formula can we use? We can use the Broglie formula, which is saying that lambda will be equal to h over mu. Here we have the speed, and we know the mass of neon. Yes, what is the mass of neon of one atom? If you check in the periodic table, you will get it in AMU, right? And in AMU, this is 20.18. But here we need the mass in kilograms. So we need to do the correspondence between 1 AMU and a gram or a kilogram. Here we need it in kilograms. So 1.18 times 1.661 10 to the power minus 27 kilogram. Okay, so this is the mass of neon. We have the speed and we know h, so we can calculate lambda. H is 6.63 10 to the power minus 34 divided by the mass, so 20.18 times 1.661 10 to the power minus 27 kilogram multiplied by the speed 2.00 10 to the power 5 meter per second. So lambda is equal to 9.89 10 to the power minus 14. So this is what you get from your calculator. Meter, we need to get it in nanometer. So it's 9.89 times 10 to the power minus 5 times 10 to the power minus 9. And this is nanometer. So lambda equal 9.89 10 to the power minus 5 nanometer. So this is the direct application of the Broglie relationship between lambda, h, m, and u. Okay. Let's move to problem number 6. Which of these ground state ions has at least one unpaired electrons? Okay, so how can we know if it has an unpaired electron? By having the electronic structure. So let's get first the Z for all of them. So we have scandium, Z equal 21. For vanadium, Z equal 23. So this is directly from your periodic table. Magnesium, Z equal 12. Phosphorus, Z equal 15. And sulfur, Z equal 16. Let's start by sulfur. So if I have S2 minus, it will be 18 electrons. I will add 2 electrons, so 18 electrons. So how can I fill them? By 1s2, 2s2, 2p6, 3s2, 3p. So here we have already 10 plus 2, 16. So I need 6 more to get 18 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. This is 18, and there is no unpaired electron here. For p equal 15, when we have p3 minus, I will add 3 electrons. So it's going to be also 18. So same configuration here, no unpaired electron. Okay, now when I have Z equal 12, if I have Mg2 plus, which is the magnesium ions, I'm removing 2 electrons, so left will be 10 electrons. So the configuration will be 1s2, 2s2, 2p6. Here again, no unpaired electron. Okay, when Z equals 23, if I have vanadium 5 plus, what do I need to do? I need to remove 5 electrons. Okay, so it's going to be 18. So here, same configuration as S2 minus and P3 minus, so no unpaired electron. Let's check the last one. If I have Z equal 21 and I have scandium 2 plus, meaning I'm removing 2 electrons, so Z will be equal to 19. Okay, so here I will have 1 unpaired electron. And we can write it, the configuration. So we'll have 1s2, 2s2, 2p6, 3s2. Here is 19 already, so 3p6. So what is coming after the 3p orbital? Yes, 4s1. Okay, so we have this one that will be unpaired. I will have half field for 4s. Okay. Okay. So let's move to problem number 7. When an electron in a 2p orbital of lithium atom makes a transition to the 2s orbital, so I have 2p orbital, an electron that is making a transition to a 2s orbital. A photon of wavelength 670.8 nanometer is emitted. The energy difference, I need to calculate the energy difference between 2s and 2p and 2s orbital. So I have here, if you remember, 1s, 2s, 2p will be somewhere here, 2p. And I have emission from this level, so 2p to 2s here. I will have a photon that is emitted and corresponding to delta E equal to hc over lambda. And here I need to calculate delta E. So delta E will be, lambda here is equal to 670.8 nanometer. And I need to convert it to meter, okay? 10 to the power minus 9. So here I have 6.63, 10 to the power minus 34, times the speed, 10 to the power 8, divided by 670.8, 10 to the power minus 9. And delta E will be equal to 2.961, 10 to the power minus 19 joule. Okay, so direct application of delta E equal hc over lambda. Our answer is A. Okay, problem number 8. Which electron configuration represents a violation of the Pauli's exclusion principle? What does the Pauli exclusion say? Pauli exclusion principle. What does it say? Okay, it's saying that two electrons cannot have all of the quantum numbers that are equals. Okay, you cannot have N, L, ML, and MS that are equal for two electrons. We will have one of them that will be different. If you look at E, so we are talking about the Pauli exclusion. If you look at E, you have 1s2, 2s2, 2p. Here you don't have two electrons that have the same four quantum numbers. Here, similarly, you have one here, 1s, 2s, 2p. Okay, you don't have two electrons that have all of the quantum numbers that are the same. One that is clear is this one. Because for this electron, they are in 2p, and they both have ms equal plus 1/2. This is not possible. Okay, this is not possible. All of this, you have other rules that are not respected. For example, here we don't have the Hund rule that is respected, because if you want to do it stably, you will have this 1, 2. Okay, this is good. 1, 2. But for the 2p, for example, here, what is better is to fill them and having to maximize the same number of spin. So the correct one will be like this. Okay, but these two electrons, they don't have the same quantum number of spin, even if they are in the same orbital. So they don't have all of the four that are equal. Okay, but they don't respect. Hund rule is not respected. But Pauli principle is respected. Here, what is the problem here? Yes, you cannot move to a higher energy orbitals if you don't fill this one. So you should fill this one first. Fill this one first. Then you will have 4 electrons. And the one left, you can put it here. So this is not correct. Okay, it's not correct. The correct configuration will be something like this. 1, 2, 1, 2. So I have 4 and 1 in the 2p. Okay, but still here, the Pauli principle is respected, but not how you fill the electron, meaning the Hund rule. Okay, stay here, it's fine. This is the correct configuration, this one. So you have 1 up. So ms equal plus 1/2. Down, ms equal to minus 1/2. 2s, you fill it, and then the last one is on 2p. So this is the correct configuration. Okay, correct configuration. Okay, this is also correct. So you fill 2, and then you fill 1s with 2, and then you go to 2s. So this is also correct configuration, meaning it respects also Pauli exclusion and Hund rule. So this is correct configuration. But this, the A, this is correct configuration, but A is completely wrong. Okay, you cannot have this plus half 2 times for 2 electrons that are on the same orbital. So this one is definitely not respected, the Pauli's exclusion principle. Okay, let's move to problem number 9. At what speed must a 3 milligram object be moving in order to have a de Broglie wavelength of 5.4 10 to the power minus 29? So here you just need to remember the relationship between lambda, h, and mu for the de Broglie relationships. So we have the mass, we have lambda, and we need to deduce the speed u. U equal h m lambda. Okay, so we can calculate u. H 6.63 10 to the power minus 34. Here, don't forget to convert milligram to kilogram, okay, by multiplying 10 to the power minus 6, okay. So we have 3.0 10 to the power minus 6, because it's minus 3 gram, and then you add another minus 3 for kilogram, multiply by lambda, 5.4 10 to the power minus 29, okay. And U is equal to 4.1 with 2 significant figures, meter per second. So our answer is A. Okay, let's move to the last problem. The correct configuration of a ground state silver atom is, so we have 5 possibilities. So what to do is, for silver, you have Z equal 47. And the noble gas that is close to it is krypton. And for krypton, you have Z equal 36. So you need to add 11 more electrons. Okay, so silver will be krypton 5s and 4d. And this is here, you have 11 electrons. So you can put 1 here and 10, or 2 here, or 5. But here will be 9. Which one is more stable between these two? This one, because you maximize 10 electrons here, and this orbital will be lower in energy. So for 5s1, 4d10, meaning this one will be the correct configuration. This is more stable. Okay, so that's it for this recitation. See you again next time.